Hi, it's time for another math easy solution. We're going to discuss further into the definition of derivative, but now look at a very interesting topic on looking to see if we can get a more general definition of this. And the reason is because in my next video I'm going over the Cauchy's mean value theorem again as a visual proof, and that one has a slightly different take on the derivative. So I'll solve that in here, and then next video will make more sense why I'm doing this. But regardless, this is pretty interesting on its own. So first thing we're going to do is recall the definition of the derivative from my earlier videos. I went over this. The derivative as a function is written as f prime of x, and that equals to limit as h approaches 0 of the formula f of x plus h minus f of x all divided by h. And again, I'll put the links to this in more detail in the video links below in the description. But basically the idea is this line right here in this graph is this function y equals f of x, and now the slope is defined as the rise over run. So when you go from a point x right here and move by an increment of h, so going up to x plus h, so that we have a run of here of h, and a rise is the difference in these y values or these f of x values. So you're rising by f of x plus h from f of x. So the rise is the difference between that, so that's f of x plus h minus f of x divided by h. And now the derivative is this same slope, but as this h value or the run approaches 0. In other words, it's the instantaneous slope. So if you were getting this h value approaching closer and closer to 0, you get a slope that approaches something like this, and this would be our f prime of x, which is the instantaneous slope at this very point. Yeah, and this is expressed using this limit. So basically the derivative is defined as the instantaneous slope. So but the thing is, in this definition, the vertical axis is y equals f of x, or just dealing with the f of x values right here, which is a function of x, and the horizontal axis is simply x right there. But what if the horizontal axis was a bit more general, was instead a more general function? We'll call that g of x. So it could be x cubed, x squared plus 3, etc. Just random functions there. How would this instantaneous slope be formulated on a different coordinate system? Instead of just x, we're going to be dealing with a new function g of x. So basically consider the following, and again, the reason I'm doing this is this will arise in my next video, so I wanted to do this first just to get some background on it. So let's just consider a general function. So this one right here, this vertical axis, we'll consider that as y equals f of x. We'll just call it f of x, and on this side g of x, like that. So if you were to plotting these, let's say we had a curve that looks something like this, and it could look like this because these are just random functions of x like that. For whatever value, you're going to have a different value there. But let's look at specifically this point right here. So I'm going to move this down a bit more. Let's just move this down here just to make it easier to write. So from here, so we're going to try to find out the same exact thing. So that's our x value, and then let's say we had our we move by an increment of h up to here. This is the x value, but the coordinate is g of x, so this is g of x like that. And then we move by an h, we increase x by h, so we get g of x plus h like that. And likewise on this side, what we're gonna get is when we increment by x, so this initial point, that's just the value x. So both of these coordinates are both of these vertical and horizontal axis functions are functions of x. So at this point right here is f of x. Now we're incrementing x by, again, h. So we're just trying to write down the same definition, but it's going to be slightly different. So this is going to be f of x plus h, like that. Yeah, so now if we were to do that same methodology as above right here, so we'll draw the rise of a run, slope. So from here to here, we get a triangle like this. It's a perpendicular. So then we have the run, and then the above is the rise. So on this graph, that's a run over rise. So then from here we can define the instantaneous slope as, I'll just write that down, instantaneous, how do you spell that, A-N-E-U-S, slope, like this. Now this would equal to the limit, as we're going to make the limit as this h goes to 0 right here, so that we're incrementing very, very small. Same thing will happen with the above. When h is really, really small, it will be very similar to whatever f of x is. So limit as h approaches 0 of the rise, and the rise is going to be on this graph the difference in the f of x value, so that's going to be f of x plus h minus f of x. So same as above, same thing as above in this formula, except now the h is different. And the reason is because the run is actually going to be g of x, the difference between g of x and g of x plus h, because that's how the slope looks like now. So g of x plus h minus g of x. So it looks something like this right here. And now what I'm going to do is, well, we have something like this. We can simplify just to get it to look like it. We can make both the top and bottom look like this. And to do that, I'm going to multiply the top and bottom, the top by 1 over h, and then the bottom by 1 over h. So that now what we could do is, these are limit properties, we could combine the limits into this division equation. So what we'll have is limit, and the reason we're doing this, we're not changing anything, these are just both cancels, it's just cancels and nothing changes. So what we'll write is the top's going to be limit as h approaches 0 of f of x plus h minus f of x, all divided by, now this h, just put it there, and then we're dividing by, because it's whenever you have a limit, you could put that in the top and bottom, the numerator and the denominator. Like I went over in my earlier videos on limits, you can see that in the video below. I think it's called the division law. Correct me if I'm wrong, but it should be in the description below. So just check that, I made a video earlier on that. So what we have here is we have this function on the top. Let's move this down to make it appear a bit better. Then divided by the limit as h approaches 0 at the bottom side, and then move this divided by h on the g of x. So what we have is this g of x plus h minus g of x all divided by h. So now what we have is, well, these are two, the top and bottom are both definition of derivatives as shown here. These are the exact same thing. So this limit h approaches 0 of f of x plus h minus f of x divided by h, that's just the f prime of x, or the derivative. And now the same thing with the bottom, except we're dealing with g prime of x. So what this means is that the instantaneous slope of this new type of graph is equal to the derivative of in terms of f, so, or in terms of x, of the f of x function. So f prime of x divided by the derivative of the g of x function. So we have this. So this is equal to the instantaneous slope. And now what's interesting is this is the more general way of looking at the instantaneous slope, but for the case where this is equal to g of x, so that's what we could consider it as, put that in bracket. So if x equals to g of x, so I'll write if, or g of x is equal to x, then the derivative, g prime of x, is simply equals to 1. So in this case, the instantaneous slope, or the derivative, instantaneous slope is equal to f prime of x divided by 1, or just f prime of x. So the basic one is so basically when the horizontal coordinate is just equal to x, that is when the basic definition of the derivative is given from. So that's this part right here, and that's one we're all used to. So I just wanted to go over this to show that when you're dealing with different functions on the horizontal axis, this is how the instantaneous slope is considered, which is also another way of saying the derivative, which is pretty interesting. So anyways, that is all for today. Hopefully you learned from this very unique and interesting topic, and hopefully you stay tuned for the next video, which is going to use this more general definition. and it's more interesting in that too. Anyways, that's all for today. If you learned, like always, you can download these exact notes in the link below, and thanks for watching, and stay tuned for another Math Easy.